Hello, everyone. Can you hear me? Can you see my screen drawings? Okay, good. Okay, any questions before we start?
Can we ask any kind of question?
Sure.
Okay, I guess I was just kind of wondering the difference between like lists and sets or bags. I guess I just really want to know, when do I use C n comma r and C n minus something plus
Yeah.
1?
Okay, yeah. So you were asking about lists, bags, and sets. So these are unordered, no repetition. The bags are, that's gonna be bad, unordered too. And they do have repetition or allow it. And lists are ordered, and you have to decide whether they have repetition or not. So your second question was, when do you use the choose r from n, or use choose n plus r minus 1 from r, right?
Yeah.
Yeah. So this one is for unordered, no repetitions. So this is like sets here. And this one is unordered with repetitions allowed. Does that make sense?
Yeah, so are those bags?
Yeah, so yeah, bags are this one. So, you know, a bag could be 1, 1, 2, something like this. Whereas the corresponding set would be 1, 2. So that's what we mean by repetition. Does that help?
Yeah.
Someone's says quiz 3 question mark. Yeah, it's graded. I was waiting for one person to finish. I'll release them when the discussions are done. Is that it? Okay. So first we'll do a couple of problems from quiz 3. Normally I would say to let you think about it, but I suppose you already have. So for this one, we have n. We have Boolean variables p0 to pn. And we have this sequence ak is equal to p sub k plus ak minus 1, where a0 is p0. And we're proving that p0 times an equals p0 for all n greater than or equal to 1. And this is by induction. So we already filled in the induction statement. So you just need to show the base case right here. So P of 1 is equal to the statement from up here. So we're trying to show A1, nope, statement right here. P0 times A0, not 0, yeah, times A1 equals P0 times, and then we apply the definition, P1 plus A0. And that's equal to P0 times P1 plus P0. And then, so these are just by definition here. And then we can apply the commutative rule to get P0 times P0 plus P1. And then that equals P0 by the absorption rule right here. Quiz 3 combinatorics. Ah, yes. Okay, any questions on this one? Okay. And then for this one, we're doing the inductive step. So we begin by writing down what P of n means. So that's P0 times AN, and that's equal to P0 times Pn plus AN minus 1. That's just by definition. And then we can use the distributive rule to get P0 times Pn plus P0 times AN minus 1. And so if we look, oh, yeah. Yes. So right here, we can apply our induction hypothesis, which says that P0 times AN minus 1 equals P0. This was by distributive. So we get P0 times Pn plus P0, right? And so that's induction hypothesis. And then we can use the distributive rule. No, actually, we need to use identity first. So P0 times Pn plus P0 times identity times 1, and that's the identity. And then we can use the distributive rule to get P0 times Pn plus P, not P0, P just 1, plus 1. And that is by distributive. And then coming over here, we can rewrite that as P0 times, and then we're going to apply universal bound. So that says P plus 1 is equal to 1. So that's turning this into just 1. And that's UB. And that's equal to P0 by the identity. Any questions on that?
Mark, just after the inductive hypothesis, you can just apply the absorption, right?
Can you apply absorption there?
Yeah, directly, like P plus PQ equals to P.
Oh, you're okay, yeah. Yeah. Oh, yeah. You do the plus 1 here.
Oh, yeah, that one.
Yeah, so you do this plus 1. It's easy to miss some rules. Yeah, so you can just apply absorption right here. So you would do a commutative. So I would get P0 plus P0 times Pn, and that's by commutative. And we look at the absorption rule, and that's just equal to P0 by absorption. Thank you. That's also a good solution. Let's see. Yeah, you can apply. So I'm looking at comments. Someone applied absorption and commutative. Yep. Can you show the base case? Okay. Missed the last part. Okay, yeah. So we got to P0 times P0 plus P1. And then we said, oh, we can apply the absorption rule to get P0. Does that help? I'll take that as a yes. Yeah, we do post these slides, so if you want to go back and look at something, you can. Oh, also we record on YouTube, so. Any other questions on that? Okay. So for this one, we're going to be doing showing that these sets, this set equality holds. So we have A is equal to pairs in pairs of integers, such that 2 divides their difference. And then another set where of pairs of integers where 3 divides their difference. And a third set, C, where for pairs of integers, 6 divides the difference. And so we're going to show that A intersect B equals C by the using an element-wise proof. So we'll begin by showing A intersect B is contained in C. So if we let X be in A intersect B, then pair XY be in A intersect B, then XY is in A, and XY is in B. And this is just by the definition of intersection. So if we look at just XY is in A, so we say XY is in A, then that means that 2 divides X minus Y. And that means that there exists an L in the integers such that X minus Y equals 2L. And then if we look at what it means for XY to be in B, we get XY is in B, and that means 3 divides X minus Y. So there exists a K in the integers such that X minus Y equals 3K. So we know that both of these are true, so we can set them equal to each other. So we have 2L equals 3K. Now, if we just look at this, we know these are both integers. And if we remember prime factorization, then it's unique, which means that the prime factors of this side are equal to the prime factors of this side. So uniqueness of prime factorization. Prime factorization. So because it's unique, we know that 2 must divide K. 2 divides K, so that means that K equals, what letters do I have left? Let's just say A. 2 times A, where A is an integer. So we can put this back in and get X minus Y is equal to 3K, which is equal to 3 times 2A. And that's equal to 6A. So remember, we're trying to show that this is an element of C as well. So if we look here, we see, oh, okay, so in order to be in C, we need to have 6 divide the difference. So this right here means that 6 divides X minus Y, and that means that XY is in C. Any questions on that? It's okay if you say, I don't get it, like anything. Okay.
Is there another way to do that? Or is that the only way to use the prime fact? Maybe. I can't remember exactly what I did, but I didn't do that.
Yeah, I mean, it's all going to boil down basically to, if you look at this side, the 3 has to be in this L, and looking over here, the 2 has to be in this K, right? Yeah, I mean, if you didn't write, you could have just said, oh, well, we have 2L equals 3K, therefore 2 divides K. That's fine. Yeah, I don't think you I'll have to look at how it was graded. I wouldn't have taken off for uniqueness of prime factorization. I hope it's graded that way. Yeah, so that's the rigorous way to say that. You could have just said that 2 divides K. Anything else?
Yeah, could you remind me what uniqueness means? Because I think I know.
Yeah, so uniqueness means that, okay, so, so if I have an n, if I have an n in the integers, and the prime factors p is equal to a set, so let's say just p0, p1, p2, right? So it has some prime factors in it. If we say that we have a set p1, or just, and then a set q of prime factors, we have p0 or q0, q0, q1, right? So we have 2 sets of prime factors. And what uniqueness means is that p equals q. So there's only one way to do it. And I should also note that 1 is not a prime number, so you're not going to have multiple 1s in there. Does that make sense?
Yeah, okay.
Yeah. Okay. Moving along. So this one we're showing C is a subset of A intersect B. And that is, we're saying, so we have X is in C. And so we apply the definition. That means that X comma Y, so that pair is in C. So we have 6 divides X minus Y. And that means that X minus Y equals 6L for some L in the integers. And if we look at this, this is equal to 3 times 2 times L. So we have X minus Y is equal to 3 times 2L, and X minus Y is equal to 2 times 3L. And you can just do that by the commutative rule on integers. So the fact I can write it this way means that 3 divides X minus Y, and that means XY is in B. And this means that 2 divides X minus Y. So XY is in A. And since both of these are true, this means that X is in A intersect B by definition of intersection. Everyone good with that? Okay. Yeah, one other thing to note is actually that if you look at this, you kind of are doing the same thing you did on the last one backwards. If you want to think about it a little more. Okay, now for our first combinatorics question. So we're finding how many binary sequences. So this means that we're putting 0 or 1 into each place in the sequence, of length at most 5 have exactly 3 ones. So so an example of one that's of length 4 would be 1, 0, 1, 1. So that's an example there. So before I tell you to work on this a little on your own, does anyone have a suggestion on how we start? Yeah. So our strings can be of length 3, 4, or 5, right? So yeah, there's no way I could get 3 ones in a string of length 2, for instance. So that's not going to happen. So you need to find how many strings there are in a string of length 3, 4, or 5. I'll give you about a minute to do that, or 2. Okay, so based on what I'm seeing in chat, there might be a step before determining which cases you want, and that's, whether we're doing ordered. So is this ordered? And do we have repetition? So if you think about it, what we're doing is we're slotting these ones into the positions in the string. So the order we slot them in doesn't matter, so it's not ordered. And do we have repetition? No. So it's unordered without repetition. So I've seen this answer. So for 3, a string of length 3, there's only one way to do this. And that's choose 3 from 3. That's equal to 1. A string of length 4, we're basically just choosing where this 0 appears. So it's choose 4, 1, or 3. Yeah, that makes sense. I guess some of you are calculating probabilities of these strings happening. And then 5, we're choosing from 5 positions, 3 of them to have the ones. So we have choose 5, 3, and choose n is always 1, so that's 1. These are just quick things. So if I have n choose n minus 1, this is equal to n. So this is equal to 4. And then 5 choose 3. I'm going to apply the definition. And that's 5 factorial over 3 factorial times 2 factorial. And that's equal to 5 times 4. So I'm going to get rid of the 3 factorial here. Divide by 2 factorial. That's equal to 20 over 2 is equal to 10. So this is equal to 10. Now, from these three, we need to think, okay, so are these completely disjoint, right? So because we have three cases, we're trying to use the sum rule. We look at them and think, okay, no, a string of length 3 is never a string of length 4, so these have to be distinct things. So we can just do the sum rule without any overlap. So we get 10 plus 4 plus 1 is equal to 15. Any questions on that? Okay.
I have a question, easy question. When do we have to convert it to like an integer like 15, or when can we leave it as just in the form C5 choose 3? I mean, I know I know that you can sometimes and that you can't other times. Will we be told to give the right, like give the calculation?
On homeworks, it will tell you if they want the number. The quiz will not require a calculator. So if you need to write down an answer, it's not going to be anything more complicated than like that. Yeah, I mean, so the problem with having you calculate it is, you accidentally calculate this as 9 and then you get 14. So when we're grading it, we have to go back and look here and say, oh, they calculated that wrong. When really what we wanted you to do was come up with this. So you're not going to have to calculate anything that's I shouldn't put mistakes in the slides, but you're not going to have anything that's really error prone. I hope that helps. Yeah, so on the exam, choose 5-3 should be fine. In fact, it makes it easier for us. Yep. But there's a reason we're calculating it in this case. So for part B, we say how many binary sequences of length 6 have exactly 4 ones. So if we look at this, using the same logic, we say, okay, we're putting 4 ones into positions in a six letter string. So we're choosing 4 of these positions to have 1. So again, it's an unordered without repetition. And so we have 6 things, and we're choosing 4 of them. And that's 6 factorial over 4 factorial times 2 factorial. This 4 factorial is 4 times 3 times 2 times 1, so I'm going to cross that part off up here to change this into 6 times 5. So we get 6 times 5 over 2. And that's equal to 3 times 5 equals 15. And that's the same as that. Does that make sense? Hopefully. So the final question asks, why are these questions the same? And so in the book, there's a theorem that says choose n. If you're choosing n from k, that's equal to choose n minus 1, k minus 1, plus choose down to k minus 1, k minus 1. So in the previous one, this is 6. And this is 4. So we're doing choose 6, 4. We can say choose 6, 4 is equal to choose 5, because we're subtracting 1, and then 4, not 4, 3. We're subtracting 1 from 4 to get 3, plus, so if we continue down, we get choose and -2, k minus 1, plus 4, 3, and then we stop at k minus 1, so we get plus 3, 3. And so that's the reason that these match up. There's actually another reason. Well, actually, this is the reason this is true in the first place. So if we look at our 6, bit position, so like bit 0, bit 1, up to bit 5. Bit 0 equals 1, or bit 0 equals 0. So if bit 0 equals 1, how many ways for this to happen? Does anyone have an idea? So I'm saying that I have the string 1, and then 5 bits after it. Yeah, so this is just choose 5, 3. Because we have 5 blank spots and we already took a 1 away. So if B0 is 0, then we're now in the case where we have 0 and then 5. Yeah, it's choose 5, 4, but we're trying to get something that looks like this. So we know this is 0 right here. We know that B1 is equal to 1, or B1 is equal to 0. So if B1 is 1, then we're choosing choose 4, 3. We're choosing 4 from the 3, right? Or we're choosing 3 from 4 because it's 1. Yep. And then if B1 is 0, so we now have 0, 0, 4, then, B2 is 1. And that, so B2 equals 1. So if we have a 1 here, then we're putting 3 and 3. And we think, okay, well, can B2 equal 0? No, because we're putting 4, so we have, this would be, in this scenario, we have 3 zeros here. And then we're trying to put 4 into 3 slots. So this is equal to 0. So in all of these cases right here, they're all disjoint because the bit is either 1 in this case, or it's 0 and another bit is 1, or the second bit is 0. So this is why this whole identity holds. Is it a formula? It is a formula in your book. I forget which page. It's like 400 or something. I don't think you'll need it on the exam. You should be able to still just calculate it out, but it is, I find it useful to understand why this works. Yeah. I think, if I'm understanding Brendan's question correctly in chat, he says, for proving, do we just have to write the top part, or do we have to show everything, or can we just write C, choose 6, 4 equals C, choose 5, 3 plus choose 4, 3 plus 3, choose 3. And yeah, because we have this theorem. You're not going to be asked to prove it. Yeah, you can just cite this theorem. Any questions on that? Yeah, so the key is, so if you don't immediately get this, just think about it. what I really want to say is that, this is the reason that this works. And if you look at Pascal's triangle, you can also see it there. So, yeah. And this is the reason that Pascal's triangle even works. Why Pascal's triangle gives you the binomial coefficients of these choose things. Yeah, so that's it. Okay, so now we're doing a bag problem that says, how many ways can 2 winners be chosen from a class consisting of just 4 people named A, B, C, and D? 1 second, I need to mute something. I'll just quit it. So we have 4 students named A, B, C, and D, and we assume that prizes are identical, so we can't tell the difference between, if A gets the prize and B gets another prize, then it's the same thing as, if we switch the 2 prizes, we can't tell the difference between the prizes. And the same person can win both. Okay, so someone want to help? Yeah, so as the problem says, we're doing an unordered list of some length, and we're using some set with repetitions allowed. So this is because it's a bag. And I'll give you a minute to think about this. Okay, so who wants to help me fill in what goes here? Does anyone have an idea?
I'd like to try. Would it be 4?
Why would it be 4?
Oh, I got myself wrong. I'm thinking 2 in that case.
Okay, yeah, it is 2. And why is it 2?
Because you can only win 2 prizes.
Yeah, because we only have 2 prizes that we're giving out. So we're just choosing 2 things from this list. Yeah. That's another way of saying the answer to this one is A, B, C, D, right? So if we look at this, so we have the number of elements in the set A, B, C, D. Close enough. This is equal to 4. So which is our R and which is our N? So because we're doing a bag problem, right? We're going to be doing N plus R minus 1, choose R. So which one is our N and R?
Okay, I'm thinking the N is 4 and the R is 2.
Correct, yeah. So that gives us choose 4, because N is 4, plus 2 minus 1, and from that we're selecting 2. And that's equal to choose 5, 2. And that's equal to 5 factorial divided by 3 factorial, 2 factorial 10, is it? Yeah. You can also do that on Pascal's triangle. Except it takes a long time to make it. 5, 10, 10, 5, 1. Yep. So 10. Can anyone think of another way to do this? So what if we just did we have two, we have the number with two distinct winners. And the number with one person winning twice. So how many ways can we do this with two distinct winners? So it's no longer a bag problem because we don't have repetition anymore. Yeah, so we're choosing 2 from 4. So 4 choose 2. And that's equal to, so this is the 4th row, 0, 1, 2, that's equal to 6. And how many ways can I have it where one person wins twice? I mean, this one's easier. I mean, yeah, 4 choose 1. And that's equal to 4. And these two are distinct events, right? So if you have 2 winners, it's the same. It's different from one person winning twice. So we do 6 plus 4 using the sum rule, and that's equal to 10. So, you know, sometimes if you're not sure, try to see if you can solve the problem another way. I find it useful in doing combinatorics if I'm not sure. Okay. Oh, apparently did we answer everything in the question? I guess so. Yeah, okay. Yeah. What do you mean by just to rewrite? Oh, okay, yeah, I see what you mean. So give us space to write down that sentence. Yeah. Oh. Well, maybe we did extra work. So we have 5 cards coming from a standard 52 card deck and lined up in a row. I hope everyone in the class is familiar with cards, and there's a definition in the book, if not. So the first part says how many lineups. So we take 5 cards off a deck. How many of them are there in which all 5 cards are red? And so you need to think about this. So order matters. So we're not using a choose function. And we're coming off a deck with 52 cards. That means that we don't have repetition. So just to remind you, we have 52 cards. 26 are red. 26 are black. I guess there's no jokers in the deck. Yeah, okay, so I'll give you a minute to think about that. Okay. So we're looking for the number of situations we can be in where the 5 cards we dealt off were from the 26 red cards. So our first card, we have 26 possible cards there. 25, because that card's no longer there. Times 24, times 23, times 22. And this is P26, 5. So we're doing a permutation with 5 elements out of a set of 26. Is everyone good with that? Okay. And then B asks us, how many such lineups are there that have at least 1 red card? So the keyword here is at least 1. So I'll give you a hint. You might want to use the complement rule on this one. So the complement rule says that for if you have the total number of events, total number is equal to the number of X plus the number of not X, right? So we can do, total of X is equal to total number minus where X doesn't happen. Yeah, that's not quite right. Yeah, so I'm seeing the right answer in chat. So if we look at this at least 1 card, that means that it can have 1 card, 2 cards, 3 cards, 4 cards, 5 cards, right? Those are possibilities. The opposite of this would be 0 cards. So if we have exactly 0 red cards, that means we have all black cards. So if we go to this rule here, we have the number of red card, the number of 5 cards with number with greater than or equal to 1 red is equal to the total number minus the number with 0 red, or equivalently with 5 black. And we look at part A and say, okay, well, the reds and the blacks are interchangeable, so we know that this one right here is equal to P26, 5, and this one right here is the total number, so we're just going over the 52 cards. So we get P52, 5. So the answer is P52, 5 minus P26, 5. That's just by the complement rule. Any questions on that? This would definitely be a problem that you are not going to write out the number on a quiz. I'm looking at the number and it has 15 digits in it or something. 9 digits, that's pretty big too. So our next one is we'll do this one here. How many such lineups are there for all cards that have the same suit? So we have 52 cards, 4 suits, 13 cards of each suit. Why is 26P1? Yeah, I'd have to think about that. I'm responding to chat. So we have 13 cards of each suit, and we want to know number of hands, 5 card even, with all one suit. So what's the first thing we want to do? Yeah, so we have 4 suits, so we have 4 possibilities. You know, we have spades, diamonds, clubs, hearts, right? It doesn't matter. We can interchange each of these. So we're going to get 4 times something. Right, so we just have to think about, for example, how many hands have four all 5 are spades. Choose from you. Again, order matters. So we have 13, for example, spades, and we're choosing 5 of them. Yeah. So that's equal to apparently 617,000. 760. And that takes us up to time. So are there any questions on that? If you want to see the other ones, I think the other TAs go faster than I do. So you can look at, watch the recordings there, and you can come to office hours if you have trouble finishing the rest of the practice quiz. Oh, one other thing is we have this problem 5. And so this one, the contrapositive is X is in A minus C, implies A and B is not a subset of C. Or, so this is the contra, or X is not in B. And your cases are going to be X is in B or X is not in B. Yeah, there's some sort of conversation in chat about explaining something that I've missed part of. So any questions before we end?
Let's see, I saw the work before. Is it true that any bad problem can be kind of translated into a set problem, or set, simple CNR?
Yeah, so you can transform bag problems into set problems. Remember, so if you think about the so if you think about it, right? So let's say we have 10 slots, or let's just do 5 slots, and we have 2 things in them. So 2 kinds of things. We say, okay, yeah, we have 0 to 5 of each of these things in the thing. So 1, 2, 3, 4, 5. This one doesn't count. So if we look here, we can have 5 total items, right? And if we say, okay, well, I'm going to draw a line between them. Yeah. You get, so this line is going to indicate, where, so if I say this part is the A half and this is the B half, then this line is going to tell you where, how many A's and B's you have. So in this case, I would have 3 A's and 2 B's. If we look at the places we can put the line, they're right here. Right? So we have n equals 4, r equals 2, 5. And we have 1, 2, 3, 4, 5, 6. So we have n plus r minus 1 equals 6. And the minus 1 is coming from the implicit ends right here. So one of these doesn't get counted. And then you just are choosing our things in there. Yeah, and then when you convert it here, you need to add 1 or subtract 1, yeah. Does that make sense? I think we're stepping into the next section. I forget, Lynn or Ilkin, do you know which section of the book gives tells you how they derived the formula for the bag problem?
No. I don't know.
Yeah, so Deverin, is that how you say your name?
Yep.
Yeah, I'll send you the section of the book, and if you have problems, you can come see Ilkin or I tomorrow in office hours or something.
Very cool. Thanks.
Yeah, okay. And YouTube. Stop. How do I stop end? Can't, no.